We will begin our study of physics with simple machines. You could justify this a couple of different ways. Historically, physics, it could be argued, began with the study of simple machines, especially the Greeks, philosophers like Archimedes. Also, there are important intuitions and concepts that we can develop in the context of simple machines that provides a very practical, everyday place to develop some intuition about physical reasoning. Again, historically, in the Renaissance, when physics really began developing again after the Greeks, a lot of the early concepts were in fact developed in the application of simple machines. People, especially in Western Europe, there and thereabouts, wanted to know how these machines work, or what would be some common principles for these machines, and how these machines related to the creation of motion. It's common to say that there are 6 different kinds of simple machines. Starting at the top left, the lever, then the incline, the wedge, the pulley, wheel and axle, illustrated here with a bucket that you might use at some sort of water well, though in everyday life, automobiles and carts of various sorts provide a more common example of wheel and axle. And the screw. These simple machines are used in 3 different ways. One is to magnify the effort, or you can magnify displacement, as in these tongs. A small displacement near the hinge produces a larger displacement further out. Or you simply redirect effort. Of course, one could magnify effort and redirect it at the same time. But these are the 3 basic uses of simple machines. In discussing the magnification of effort, it's useful to define the concept of mechanical advantage. And it's just the ratio of what if you exert a certain effort, how much can you get out? And the mechanical advantage can be smaller than 1 or greater than 1, or even equal to 1. And then all 3 of those cases can be useful. So the little diagram here indicates sort of a generic simple machine. There might be some stuff hidden in that box, gears, levers, various things, but basically you exert some force on the left and you get some force out on the right. And the ratio of those 2 forces, as shown, is the mechanical advantage. Now this brings up the point of what do we mean by force? One way that you could use to define a system by which to measure force is to use weights, starting with a standard weight, which might be a 1 pound. By definition, you've got an object that is 1 pound. Now we can construct a lever, as shown, that is symmetrical. So if there's any justice in the world, if you manage to modify the weight on the right, W, either by adding or subtracting material, when the 2 balance like this, if there's any justice in the world, W will in fact also be a 1 pound weight. And then you can proceed to get a 2 pound weight and so forth. It's worth mentioning at this point that there's an interesting fact about levers, and that is that only what you might call the perpendicular distance matters. In this situation here, even though it is not symmetrical, and one might imagine that you would not have equilibrium here. In fact, it is a matter of experience. As long as the solid black lever arm, that bent lever arm, is very, very lightweight in comparison to the two weights at the ends, that in fact you have a balance in this case as well. What it amounts to is that you draw a line in the direction of the weight, up and down, the direction that the weight exerts its influence, and you do a dotted line, and you find the distance. Along that dotted line, you find the point that's closest to the axis of rotation, the fulcrum there, and that distance is what counts. So it is, again, a matter of experience, not subject to deduction in by some symmetry argument, but as a matter of experience. This particular lever would also be in equilibrium. Once we have a system of weights, we now have a way of defining or measuring, really, a mechanical advantage. You simply hang weights off the input and the output, and you see to it that they're, you adjust the weights so that they're in equilibrium. So we imagine here on the left that hanging 10 pounds there and hanging 25 pounds on the right, that the machine doesn't do anything. It doesn't go up or down. Neither of these weights goes up or down. Once we have such a situation, then the ratio of one weight to the other gives us the mechanical advantage. And you can see that, well, okay, if I got rid of the 25-pound weight, then what you could do is use that stick that's on the right. Now you could exert an upward force of 25 pounds by pulling down with 10 pounds of force on the left. But a useful way of thinking about determining mechanical advantage is to actually seek a situation like this in which the simple machine is in equilibrium. Now, one other thing we will assume for the purposes of it's simplicity, in searching for principles, we'll search for cases, or we'll assume that friction is minimized. And in fact, we'll go ahead and assume that we have no friction to deal with. Now, one way to define that experimentally is with the concept of reversibility, which is very important in the study of thermodynamics as well. But in any case, reversibility here means that once we've achieved equilibrium, if we were to, in a perfectly reversible simple machine, if we were to put a grain of sand, say, on the 10-pound weight, then the machine, the 10 pounds would go down and the 25 pounds would go up. Not necessarily by equal amounts, that depends on the machine. But the grain of sand would be enough to cause a non-existence of equilibrium. Now, that's pretty rare, though there are actually, nowadays, with the advent of quantum mechanical manipulation of matter, we actually have cases, a phenomenon that we can control, which are in fact without friction. For example, we can eliminate electrical resistance completely in a piece of metal, or at least certain pieces of metal. Not approximately zero resistance, but absolutely zero resistance. So this isn't as far-fetched as you might think, but it was certainly out of the reach of medieval and Renaissance experimenters. Nevertheless, it is remarkable that this assumption of idealism, that going for the consideration of ideal simple machines, even if they don't exist, actually proves to be very useful. And it is precisely this pursuit of the ideal case that led to the development of modern physics and modern engineering. It's not an obvious thing that being so idealistic would prove to be so practical, but it turns out to be the case. In any case, we shall assume our machines are without friction and are perfectly reversible in this manner. Although traditionally we say that there are six different kinds of simple machines, a moment's reflection and just comparison, a visual comparison, shows us that in fact some of them bear a striking resemblance to each other, and in fact must operate according to the same principles. For example, if you look in the upper right there, the wedge. The wedge, it would seem, is simply a movable inclined plane. So if we're classifying machines according to the different principles, rather than the more detailed geometry of the machine, we would knock this one out, saying, well, we can understand wedges by simply using using inclined planes. If we can understand inclined planes, then we can understand wedges. Also, a screw there in the bottom right is evidently just an inclined plane wrapped around a cylinder. So again, if we can understand how inclined planes work, then we can develop a theory of how screws work. So we'll eliminate that as a separate kind of fundamental machine. Now, finally, for now anyway, the wheel and axle as depicted there is evidently just a lever that sort of rotates continuously, so that the moment arm or the lever arm is continually redefined. So we get rid of these three and recognize that they are all instances either of an inclined plane or a lever. And one could also, I guess, eliminate the lower left is just illustrating redirection. So that is evidently just a balance, a equal armed lever. So the only two things we're left with then are the lever, that's the upper left, and the inclined plane. And it is not obvious that these two actually operate by the same principle. But in fact, we will see that they do. We'll begin with the lever action. Aristotle came up with a formula to describe equilibrium, or to describe a lever and that's in equilibrium. In this situation here, hanging the weight W1 at one end, W2 at the other, there will be equilibrium if that distance L1 times W1 equals L2 times W2. That number is actually sometimes called the torque that's being exerted by the weight in question. People, since Aristotle on, people have thought that they have come up with mathematical proofs of this equation, sometimes, in fact, convincing themselves that they have. But in fact, this is not the case. This is something which is simply as a matter of experience. Here, yes, and sometimes L1 is, that distance, that perpendicular distance to the line of action of a weight is called the moment arm. There we go. And the product, as I mentioned, is called the moment, or torque. We can take Aristotle's law of the lever, or lever, I never can decide how I want to pronounce that, and turn it into a formula for the mechanical advantage of the lever. We choose one of the weights sort of arbitrarily, our choice to be force in this case I chose W2 to be the applied force, and the ratio of W1 divided by W2 can be obtained in terms of the lengths of the moment arms just by a little simple algebra. In And this is pretty interesting, I think. Weight is something you can't see. Now, you can see the weights, the objects themselves, but the weight of the object itself is an invisible thing, which you perceive when you hold the thing up, but it's not something you can see with your eyes. But we can find then here an expression for the ratio of weights in terms of the ratio of some two things that we can actually measure, that we can see and measure, namely the lengths of the moment arms. Now let us attack the mechanical advantage of an incline. Now, of course, if you hang 10 pounds at P, then the tension in the rope is 10 pounds, and so 10 pounds is exerted on the weight Q. So, that exerted weight on Q, we will not consider that to be the weight out, because then that would give it a mechanical advantage of 1 in all cases. From a practical point of view, the point is that if say we might put 10 pounds at P, that might be able to support and be in equilibrium with 20 pounds attached at Q. So a good definition of mechanical advantage, a practical definition, is the ratio of that weight Q that can be suspended by means of the weight P hung at the other end of the line or the rope. My father was a sailor, so sometimes I grew up hearing ropes called lines. We'll now use conceptual reasoning to show that an incline, in fact, is just a lever in disguise. So we're going to do that by introducing an additional lever, a lever in addition to the inclined plane, which can be real or simply imagined. The main thing is that it's the lever, little b, is of negligible weight, so it doesn't add any forces to the situation. We also will construct, well, let's see, I should mention then that so we have this bar, weightless bar, little a, little b. Little b is a rotational axis that's fixed, and the bar is free to rotate about lowercase b. Lowercase a is where the bar is attached to the weight Q, and it's free to rotate about, the Q is free to rotate about that point A. Now, we will it will be useful to add some imaginary dotted lines as shown. A vertical line passing through the point A, the center of the weight Q, and a horizontal dotted line passing through the rotational axis lowercase b, and they intersect at the point C. Now, a critical thing here to recognize is that the imaginary triangle lowercase a, lowercase b, lowercase c is in fact similar to the actual geometrical measurable triangle that constitutes the lever, uppercase A, uppercase B, uppercase C. Those two triangles are in fact similar. There are probably a number of ways of showing this. I'll let you invent your own, or you can just take it as intuitively acceptable that these triangles are similar. All right, we've drawn two arrows representing the action of the weights P and Q. If there's 10 pounds attached at P, then clearly there'll be 10 pounds acting along the rope there at the location of Q, and I've labeled that blue arrow then P to represent the action of the weight, the hanging weight on the object Q. Also, of course, there will be the weight of the object. I'll go ahead and put the Q down there just to indicate, so that arrow then and the letter Q represent the action of the weight of the object Q. Now, in the absence of friction with just the original incline, the sole purpose or effect of the incline is simply to keep the object Q from moving in a direction that's perpendicular to the incline. But now, with the attachment of the rod, little a, little b, with that lever itself is capable of preventing that motion. So there is nothing preventing us from simply removing the incline. In this system, then, if the original incline system was in equilibrium, then this lever system must also be in equilibrium. But now we can say for equilibrium that our equilibrium is rotational and has to do with this lever. And so we can simply say that the moments exerted by the weights P and Q must cancel. We will need the moment arms. Consider the moment arm of the force P. P is in fact perpendicular to the rod AB. So in fact, that distance A to B is in fact the moment arm of P, and the moment or torque then exerted by the force P is going to be simply the weight or force P times that distance, the moment arm. Now, to get the moment arm of force Q, we have to be a little more careful. It's not a perpendicular angle there between AB and force Q. We've got to go ahead and draw our dotted line through the point of application. It's that vertical dotted line. And as we travel upwards along that dotted line, the point that's closest to the rotational axis, located at lowercase b, is in fact point C. So that distance BC is the moment arm of Q. So the torque is just going to be the product of Q with that moment arm, and we might put in a minus sign just to indicate it's in the opposite direction, just to note that P is trying to pull the lever in one direction, and Q is trying to rotate it in the opposite direction. Yeah, and of course this is sort of a peculiar sort of lever. There's only one, the lever exists only on one side of the rotational axis, but nevertheless it's still a lever. So here in the upper right are two expressions for the torques exerted by the weights P and Q. They must add to 0, or which can be arranged to the equation there, the third line, Q times BC equals P times AB. Now, we can again use very simple algebra to obtain the ratio of the weight Q to the weight P. That then is equal to the distance lowercase a, lowercase b, to the distance lowercase b to lowercase c. Now, though, remember the triangles formed by the lowercase letters is similar to the triangle formed by the larger case letters, the actual original incline. So we can replace then the lowercase letters with uppercase letters. Now that distance AB, uppercase A, uppercase B, is in fact a distance along, I think it's the horizontal distance. No, it's the actual hypotenuse of the incline. So we have now then derived an expression for the mechanical advantage. One might say we have derived a theoretical value for the mechanical advantage, which we can calculate by measuring the dimensions of the incline, and we can compare that with the experimental mechanical advantage by actually manipulating weights P and Q to obtain equilibrium. It turns out the theory works. So we have succeeded in understanding the mechanical advantage of an incline by using the principle of the lever. So, in our list of fundamental machines, we find then that the incline is equivalent to an imaginary lever. And so we can eliminate the lever, or the incline rather, as something entirely different from the lever action. So now we're left with these two simple machines on the far left. Now the pulley, as I mentioned before, that pulley is just redirecting motion. So that by itself is really just a lever, but sometimes pulleys are compounded. So that leads us to, one might think, to a different sort of principle might be necessary to understand pulleys. I'll try to illustrate what I mean. Let's look at a more of a compound pulley situation. We'll explore it in terms of a question. If we have this situation as shown here with frictionless pulleys, if A weighs 24 pounds, what does B have to be to achieve equilibrium? Well, probably the easiest way to understand this is just to recognize that object A, or the pulley connected to A, is being supported by two lines, so to speak. It's got the rope is acting up, serves to support it in some sense twice. So if there's a tension of 10 pounds in the rope, then there's 20 pounds of force acting upwards on A. And the tension in the rope, in this case, is going to be equal to the weight of B. So B can support then twice its weight. So if A weighs 24 pounds, to achieve equilibrium, B would just have to weigh 12 pounds. Here it is illustrated with T representing the tension in the rope. And so you can see then that 12 pounds will do it. There are two T's acting upwards on A, and B is successful in creating 1 T of tension. Now, most compound pulleys can in fact be understood. Most, if not all, compound pulleys can be understood in this way. But this appears to be sort of a whole different principle than the lever. We're going to try to make a connection between the pulley systems and the lever systems by making use of a new concept of great practical importance. That concept is the concept of center of gravity. Now, if the formulas bother you, don't worry about it. In a few slides, I'm going to show you how to work sapling problems with numerical examples. But a lot of you have had a little algebra, so you can see, you can appreciate this formula. It's the center of gravity is just literally a weighted average of the position of the various masses that comprise a system. In addition to the x position of the center of mass, you can talk about the altitude or y coordinate of the center of mass. And again, it's just, it's sort of an average position of all the particles that make up the system, but each particle is weighted according to its weight. Again, if the formula give you indigestion, don't worry about it too much. The main point is based on our definition of the center of gravity. You can use essentially the same formula, only if you substitute in changes in the positions of the various objects into the formula, you get the change in the center of gravity. We'll now illustrate that with a couple of problems that are very similar to the problems that appear in the sapling, problem set 2. So we suppose we have a frictionless pulley, and there on the left-hand side, weight A is 3 pounds, weight B is 2 pounds. Now, if weight A is made to ascend 4 inches, and so B goes down by 4 inches, what is the change in the altitude of the center of gravity? Well, here's the formula. You just, the weighted average of the vertical position. So it's going to be the weight, 3 pounds, times the position, the change in position, rather, which is 4 inches, plus 2 pounds, the weight of the other particle, B, times its change in position, which is negative 4 inches, since it's going down. And we divide by the total weight, 5 pounds. If you work that out, you get a 4/5 of an inch, positive 4/5 of an inch, meaning that the center of gravity increased in altitude. One thing to notice is that if we were to release these weights from rest, this would not happen. Weight A would not go up and B go down. And so the center of gravity, in fact, would not increase in altitude. This just doesn't happen. It's based on our experience. So let's consider what happens if A goes down by 4 inches and B goes up by 4 inches with the same weights. Well, if you just go ahead and plug in the numbers, you see 3 pounds times negative 4 inches, since A is, we're supposing, is descending, going down by 4 inches. And then B, the 2 pound weight, is going up by 4 inches. In that case, you get negative 4/5 of an inch. So in this case, the center of gravity descends. This example illustrates Torricelli's principle of statics. Torricelli was a student of Galileo. He stated the equilibrium exists in a machine when, on a displacement being imparted to it, the center of gravity cannot descend. Let's apply this to the operation of a lever. If we have a lever, as shown here, if it's to be in equilibrium, the center of gravity, the horizontal center of gravity, must be over the fulcrum, because otherwise, if the lever rotates, it can rotate in such a way as to lower the center of gravity. It's only right there at that blue fulcrum that the position of the center of gravity would not change. So if we go ahead and use that formula, and right now we're taking x equals 0 to be the 0 of the horizontal axis. So we'll let L1 be a positive number, so that the position of weight 1 is negative L1. So we go ahead and substitute in for x1 and x2. and we demand that that formula, negative L1 times W1 plus L2 times W2 divided by the sum of the two weights, must be 0 for equilibrium. Well, then we just get Aristotle's law of the lever. So from Torricelli's principle, we can actually derive Aristotle's principle of the lever. And as sort of a corollary to this principle, we see that if we release a machine from rest, if it can move in such a way that the center of gravity is lowered, in fact, that's what it does. So in this case, we have two equal weights. So by symmetry, the center of gravity has to be right in the middle. And so if the fulcrum is placed off to the left like that, then in fact that X, the X marks the center of gravity. You could see then if it rotates in the way shown there, the center of gravity diminishes in altitude. And so it is not in equilibrium, and when released from rest, it will, the left-hand side goes up and the right-hand side goes down, because that lowers the center of gravity. We can now solve problem 3 of problem set 2. Here's a very similar problem. We have a stiff board balanced in the middle. So even if the board has weight, the center of gravity of the board's right over the fulcrum, so we can ignore any change. That point will not change in altitude. So 8 pounds there on the left, and we've got 5 feet from the fulcrum. 6 pounds on the right, 8 feet from the fulcrum. We cause the 8 pounds to go down by 5 inches. Now, that may be what it wants to do, or we may have to push it down. We'll find out by calculating the change in the center of gravity. Let's go ahead and do that using our formula. The weighted average of the change, 8 pounds times negative 5 inches, since 8 pounds is going down, plus 6 pounds times the altitude change of the 6-pound weight, but that's not going to equal to 5 inches in this case because of the different lengths, 8 and 5. So you can tell it's going to go up more. The 6 pounds will go up more than the 8 pounds goes down. So it's 8/5 times 5 inches. If you work all that out, of course we divide by the total weight of 14 pounds. If you work it out, you get 4/7 of an inch, or Sapling wants you to enter decimals, so you would convert that to 0.571 would probably be good enough. So let's see how Torricelli's principle of statics works for pulleys. See if we can understand pulley systems with that. First, let's examine a system here using the usual tension in the rope technique and the number of supporting ropes. You can see if we have 1 pound there at the bottom, it's supported by 2 1/2 pound forces, and each of those supported by a couple of quarter-pound forces. So you can pull on the far left there with only 1/4 pound and support the 1 pound force. Let's see if Torricelli's principle can give us the same result. Okay, so now let's suppose that the what we'll call the load on the right-hand side, the L pounds, increases its altitude by 1 inch. Now the dotted lines illustrate that in order to have the L go up by 1 inch, we have to eliminate 4 inches of rope between the upper and lower sets of pulleys. Of course, that happens not by cutting those inches out there, but rather by P, the pull, if you will, going down by 4 inches. So we have the center of gravity changing due to the lowering of P and the raising of L. And so let us calculate those, and we require for equilibrium that the two effects cancel. lowering the weight p by 4 inches by our definition of center of gravity is just that distance, 4 inches times p. Now technically it's negative, but this is the magnitude. And we, of course, divide by the sum of the two weights. Now L it goes up by 1 inch, so there's the change in center of gravity due to the change in the altitude of L. In order that we have equilibrium, those two must cancel. So we set them equal, and we obtain that the load L is equal to 4 times P. Torricelli's principle applies not only to machines, but in fact to all objects. And this, in fact, gives us a simple visualization of stability conditions. For example, suppose we have this blue box on the blue incline, and there's friction, so it won't just slide down. And we're wondering, will it tip over about the pivot point shown there? Well, if the center of gravity of this box is at point A, then in order to tip, that center of gravity would have to go up to point B, which is at a higher altitude. Well, Torricelli's principle tells us that will not happen. Now, point C, on the other hand, if the center of gravity is there, then if it starts to tip, immediately the center of gravity is lowered. And so, in fact, if the center of gravity is at C, it will tip over spontaneously. Now, point B is sort of a special case. Any point along the line there, if that is where the center of gravity is, if the center of gravity lies along the dotted line, then it's right at the hairy edge of being stable, unstable. You know, that's sort of a special case that, you know, it's, you want to avoid that in practical situations. Using Torricelli's principle, you can see that here that the box which is going to tip over, the box that's unstable, is in fact case C. So we have found that Torricelli's principle of statics actually can be used to explain the operation of all simple machines. And in fact, there are any combination of these then also. This illustrates rather well, I think, the way physicists like to think. Einstein put it this way: in physics, we try to devise the simplest system of thought which binds together all the facts.